Welcome to this exploration of the universe, where we will unravel how the greatest discovery about cosmic expansion reshaped our understanding of the cosmos forever. At the dawn of the 20th century, most astronomers believed that the Milky Way was the entire universe, a single grand collection of stars surrounded by infinite darkness. The idea of other galaxies existing beyond our own was controversial, with fierce debates among leading scientists who wondered whether the faint smudges of light captured in telescopes were clouds of gas or vast star systems like our own. This debate reached its climax in 1920 during the famous Shapley-Curtis debate, where astronomers Harlow Shapley and Heber Curtis clashed over the scale of the universe and the nature of spiral nebulae. It was Edwin Hubble, working at Mount Wilson Observatory in California with the world's most powerful telescope of his time, the 100-inch Hooker telescope, who would settle the argument with undeniable evidence. Hubble studied the Andromeda Nebula, carefully identifying Cepheid variable stars which Henrietta Leavitt had shown could be used as standard candles to measure distances across space. By measuring the brightness cycles of these stars, Hubble determined that Andromeda was far too distant to be part of the Milky Way, revealing that it was a galaxy in its own right. This discovery shattered the old worldview and expanded the universe overnight, showing that the Milky Way was just one galaxy among countless others stretching into the deep unknown. Yet Hubble's greatest breakthrough was still to come as he turned his attention not only to the existence of galaxies, but to their motion across the heavens. He examined the light from galaxies using spectroscopy, studying how their wavelengths shifted toward the red end of the spectrum, a phenomenon now famously known as redshift. Redshift meant that galaxies were not standing still but moving away, stretching the light waves as they traveled across the expanding fabric of space itself. The more distant the galaxy, the greater its redshift, suggesting that not only were galaxies retreating, but their speed of recession increased with distance. In 1929, Hubble published his results in what would later be known as Hubble's law, forever transforming cosmology by proving that the universe itself was expanding. This law states that the velocity of a galaxy moving away from us is proportional to its distance, a simple but profound mathematical relationship that became the cornerstone of modern cosmology. The discovery that the universe was expanding overturned centuries of assumptions and raised deep questions about the origins of everything we see in the cosmos. Albert Einstein himself had once introduced a cosmological constant into his equations of general relativity to preserve a static universe, but Hubble's results forced him to call it his greatest blunder. With the revelation of an expanding universe, cosmologists realized that if space was stretching outward now, it must have once been compressed into an unimaginably dense and hot beginning. This insight laid the foundation for the Big Bang theory, which would later be refined by scientists like Georges Lemaitre, a Belgian priest and physicist who independently predicted expansion before Hubble's observations. The concept of a universe with a beginning shocked both scientists and philosophers, challenging ancient beliefs about eternity and forcing humanity to rethink its place in cosmic history. Hubble's discovery of cosmic expansion not only gave us a dynamic universe, but also unlocked the possibility of predicting its future, a question that still drives astronomy today. When Albert Einstein published his general theory of relativity in 1915, he provided not just a new way to understand gravity, but a framework that could describe the behavior of the entire universe. General relativity described space and time as a single fabric called space-time, which could be curved and shaped by the presence of mass and energy. In Einstein's vision, gravity was no longer a mysterious invisible force pulling objects together, but rather the result of matter bending the very geometry of space-time itself. Einstein's equations worked brilliantly when applied to local systems like the orbit of Mercury, which had long puzzled astronomers with small deviations that Newton's laws could not fully explain. But when scientists tried to apply general relativity to the entire cosmos, a strange problem appeared. The equations predicted that the universe could not remain static but must either expand or contract. This was deeply troubling to Einstein, who believed at the time that the universe was eternal, unchanging, and fixed like the stars in the night sky. To counteract the tendency of gravity to pull everything together and collapse the universe, Einstein introduced an additional term into his equations called the cosmological constant. The cosmological constant acted like a repulsive force, a kind of cosmic pressure pushing outward to exactly balance the inward pull of gravity, maintaining a stable and static universe. For a time, this seemed like an elegant fix, but it was a fragile balance. Any slight change would tip the universe toward expansion or contraction anyway. Many astronomers accepted Einstein's static universe because it aligned with centuries of philosophical and scientific tradition that imagined the cosmos as eternal and unchanging. However, other solutions to Einstein's equations soon emerged from mathematicians and physicists who took the equations at face value without adding the cosmological constant. In 1922, Russian mathematician Alexander Friedmann published models of the universe based on Einstein's equations that naturally expanded or contracted depending on initial conditions. Friedmann's solutions demonstrated that general relativity, if interpreted directly, already allowed for a dynamic universe without the need for a cosmological constant. At first, Einstein dismissed Friedmann's work, believing there must be an error in his calculations, but later he acknowledged that the math was sound and that the possibility of an evolving universe was real. Not long after, in 1927, Belgian physicist and priest Georges Lemaitre independently derived similar solutions, proposing that the universe was expanding from a primeval atom, a concept that foreshadowed the Big Bang. Lemaitre's idea was radical, suggesting that the universe had a definite beginning rather than existing eternally, a notion that many scientists found philosophically unsettling. Einstein himself met with Lemaitre and acknowledged his brilliance, but famously told him, "Your calculations are correct, but your physics is abominable," showing how resistant he was to abandoning the static universe. It would take Edwin Hubble's observations of redshift in 1929 to finally convince Einstein that the universe truly was expanding and that the cosmological constant had been unnecessary. Einstein later called the cosmological constant the greatest blunder of his career, though modern cosmology would eventually revive the idea in a new form to explain dark energy. The early misunderstanding about the universe's stability showed how even the greatest minds can be limited by philosophical expectations, and how evidence can overturn even the most elegant theories. The expansion of the universe is not something we observe from a privileged vantage point outside the cosmos, but rather from within the Milky Way itself, watching as every other galaxy appears to move away from us as though we occupy the very center of creation. Yet this illusion is not unique to our location, for if we could transport ourselves to a galaxy billions of light years away, we would witness the same spectacle of retreating galaxies, proving that expansion is not about one chosen place, but about the very fabric of space stretching everywhere at once. What Hubble revealed and what subsequent generations of astronomers confirmed is that the recession of galaxies is not like objects flying through pre-existing space, but rather like raisins embedded in dough rising in an oven, where every part of the dough expands and carries the raisins further apart. From the Milky Way, we see the glow of galaxies so distant that their light began traveling toward us billions of years ago, crossing a universe that has itself changed and grown during the journey. Each photon that reaches our telescopes is a messenger from a younger cosmos, a silent witness to epochs when galaxies were closer together, stars were newly forming, and the fabric of space was denser. The redshift we measure is not a simple Doppler effect from galaxies rushing away, but the stretching of space itself, which lengthens the very waves of light, leaving us with a cosmic record encoded in faint colors. Through instruments like the Hubble Space Telescope, the Sloan Digital Sky Survey, and radio observatories, peering across frequencies invisible to the eye, humanity has built a map of the expanding universe that grows richer with every observation. The observable universe is not a fixed stage but a moving horizon, one that grows as light from ever more distant regions finally arrives, carrying with it the story of formation and change written in energy and matter. Every distant galaxy is both an island of stars and a time machine, showing us what it looked like when the universe was far younger, for to look far away is also to look far back. From the Milky Way we are privileged to glimpse quasars that blazed when the cosmos was only a fraction of its current age, their light spanning more than 13 billion years to reach us, whispering secrets of the early universe. The farther we look, the greater the redshift, until galaxies become faint smudges, barely distinguishable from the background, reminders that the observable universe is bounded not by walls, but by the finite speed of light. In this grand framework, expansion is not a metaphor or a mathematical abstraction, but a directly observed phenomenon etched across the skies, connecting theory with the tangible evidence of starlight and structure. Observing the universe from Earth reveals galaxies of all shapes and sizes receding in every direction, their light stretched by the expansion of space itself, providing an immediate testament to the dynamic nature of the cosmos. The Hubble Space Telescope captures faint galaxies whose photons began their journey billions of years ago, allowing astronomers to study the universe when it was only a fraction of its current age. Surveys like the Sloan Digital Sky Survey map the positions and motions of millions of galaxies, revealing patterns such as clusters, voids, and filaments that trace the large-scale structure of the universe. By examining the redshift of galaxies at varying distances, scientists determine how quickly different regions of space are expanding, confirming that this expansion is uniform across the observable universe. Quasars, the bright cores of distant galaxies powered by supermassive black holes, provide luminous markers that trace the growth of structure over cosmic time. The light from these ancient objects travels through vast stretches of intergalactic space, sometimes interacting with clouds of gas, leaving absorption lines in the spectra that reveal chemical composition and motion. Cosmic microwave background radiation, first detected by Penzias and Wilson in 1965, offers a snapshot of the universe just 380,000 years after the Big Bang, encoding temperature fluctuations that seeded galaxies and clusters. These minute variations in the CMB temperature allow cosmologists to measure the density, curvature, and expansion rate of the early universe, giving insight into its long-term evolution. Large telescopes such as ALMA observe the cold gas in distant galaxies, revealing how star formation progresses in regions billions of light years away, providing a complementary perspective on cosmic history. Light from supernovae in distant galaxies serves as a cosmic yardstick, with Type 1a supernovae providing remarkably precise distance measurements that confirm the acceleration of the universe's expansion. Gravitational lensing, the bending of light by massive clusters of galaxies, magnifies distant objects and allows astronomers to probe regions that would otherwise remain invisible, revealing the distribution of dark matter. Radio telescopes map hydrogen across billions of light years, tracing the skeleton of the cosmic web, where galaxies form along filaments, while vast voids remain almost empty of matter. Each new observation confirms that the universe is not static but dynamic, with space itself stretching continuously, carrying galaxies apart in a process that has persisted for over 13 billion years. The combination of optical, radio, and microwave data gives a multi-dimensional picture of the cosmos, allowing scientists to cross-check distances, motions, and the evolution of structure over time. Even subtle anisotropies in the CMB reveal how tiny quantum fluctuations in the early universe grew into the vast clusters, superclusters, and voids we observe today, illustrating the link between the very small and the cosmic scale. Observing these patterns from Earth or space-based telescopes provides a constantly updated map of the universe's expansion, showing how every galaxy participates in this grand cosmic motion without requiring a center. The evidence of expansion is not limited to visible galaxies. high redshift objects in infrared and ultraviolet surveys show the same stretching of light, confirming the universality of Hubble's observations. By compiling these diverse lines of evidence, spectroscopy, supernovae, gravitational lensing, CMB, and radio surveys, astronomers create a coherent picture of the universe as a dynamic, evolving entity that has been expanding for billions of years. Even when we observe regions billions of light years away, the principles remain consistent. Every photon tells a story of expansion, of space stretching, and of galaxies being carried farther apart with time. After decades of debate, astronomers accepted that the universe was not fixed but dynamic, a revelation that overturned centuries of thinking about a timeless cosmos. Georges Lemaitre proposed a radical model in which the universe originated from an extremely dense and hot primeval atom, a concept that laid the groundwork for the Big Bang theory. The Big Bang model described a universe that began in a singular state and has been expanding ever since, providing a framework that accounts for the abundance of light elements and the large-scale structure observed today. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, a faint, uniform glow of radiation filling the universe that matched predictions from the Big Bang model. This residual radiation acts as a fossil record of the early universe, revealing a time when photons last scattered off matter roughly 380,000 years after the initial expansion began. Measurements of the CMB slight temperature fluctuations show how initial density variations grew into the galaxies, clusters, and cosmic web we observe billions of years later. The shift from imagining a static universe to accepting a dynamic, evolving cosmos was accelerated by these observations, which provided tangible, measurable evidence that space itself was stretching. Physicists used these data to refine models of cosmology, confirming that the universe had a finite age, roughly 13.8 billion years, and that its early expansion set the stage for all subsequent structure formation. Even tiny anisotropies in the CMB provide insight into fundamental physics, including the density of baryonic matter, and dark energy, all of which influence the universe's expansion rate. The Big Bang model, supported by the cosmic microwave background, also explains the observed abundance of hydrogen, helium, and lithium, elements formed during the first few minutes of nucleosynthesis. Observations across multiple wavelengths, from radio to X-ray, consistently confirm predictions of the Big Bang model, revealing a cosmos that began hot, dense, and uniform, but evolved into a vast tapestry of structure. The CMB's uniformity across the sky with temperature variations of only a few parts per 100,000 is evidence of a highly isotropic early universe, supporting the theory that expansion occurred from a singular origin. By studying the CMB alongside galaxy surveys and supernova measurements, astronomers can trace the expansion history of the universe, providing constraints on the Hubble constant and the nature of dark energy. The realization that the universe is dynamic transformed our philosophical understanding as well, showing that time itself has a beginning and that cosmic evolution is a continuous, measurable process. Cosmic expansion is not merely a theoretical concept, but a directly observable process, confirmed by multiple independent lines of evidence, with the CMB serving as the clearest proof that the universe was once smaller, hotter, and denser. The Big Bang framework allows us to connect the faint whispers of ancient radiation with the formation of galaxies, the distribution of matter, and the large-scale structure visible today, creating a cohesive narrative of cosmic history. By reconciling Einstein's equations with Hubble's observations and the discovery of the CMB, scientists move beyond misconceptions about a static universe to embrace a model that predicts both past and future cosmic behavior. The dynamic universe revealed by these discoveries emphasizes that space itself is an active participant in the cosmos, carrying galaxies apart, influencing the flow of time and shaping the evolution of all cosmic structures. Even as we measure the faint echoes of the Big Bang across the sky, the universe continues to expand, a reminder that what we observe today is a snapshot within an ongoing story billions of years in the making. In the late 1990s, astronomers were stunned to discover that the expansion of the universe was not slowing under gravity as expected, but instead accelerating, an observation that would redefine cosmology. This unexpected acceleration emerged from careful measurements of Type 1a supernovae in distant galaxies, which act as reliable standard candles for determining cosmic distances across billions of light years. By comparing the apparent brightness of these supernovae with their redshift, researchers realized that faraway galaxies were fainter than anticipated, indicating that the universe's expansion had sped up over time. Two independent teams, the Supernova Cosmology Project led by Saul Perlmutter and the Higher Z Supernova Search Team led by Brian Schmidt and Adam Rice, confirmed this astonishing result almost simultaneously. The data implied the existence of an unknown form of energy uniformly permeating space, exerting a repulsive effect that counteracts the gravitational pull of matter and drives the acceleration of cosmic expansion. This invisible energy, now called dark energy, accounts for approximately 70% of the total energy density of the cosmos, fundamentally altering our understanding of the universe's composition. The discovery of cosmic acceleration earned Saul Perlmutter, Brian Schmidt, and Adam Riess the 2011 Nobel Prize in Physics, highlighting how Type 1a supernovae could illuminate the most profound questions about the universe. Prior to these findings, astronomers assumed that gravity would gradually slow expansion, possibly culminating in a big crunch, but dark energy introduced a radically different scenario where the cosmos might expand forever. Type 1a supernovae are particularly valuable for these studies because they reach nearly uniform peak luminosities, allowing scientists to compare distances accurately across vast cosmic scales. By combining supernova observations with measurements of the cosmic microwave background and large-scale structure, astronomers could constrain the properties of dark energy, including its density and equation of state. The precise nature of dark energy remains one of the greatest mysteries in physics, with hypotheses ranging from a cosmological constant, as Einstein originally proposed, to dynamic fields that evolve over time. Even subtle differences in Type 1a supernova measurements can yield profound insights into the acceleration rate, helping researchers refine models of the universe's future expansion. The acceleration of the universe implies that distant galaxies will eventually recede faster than the speed of light relative to us, rendering them invisible and isolating local clusters in an ever-expanding cosmic void. Cosmologists now incorporate dark energy into the standard model of cosmology known as lambda CDM, where lambda represents the cosmological constant associated with this mysterious energy component. Supernova surveys continue to refine the Hubble diagram, measuring luminosity distances versus redshift with unprecedented precision, offering a direct window into the universe's acceleration history. Type 1a supernovae also allow comparisons of nearby versus distant explosions, showing that acceleration is a recent phenomenon in cosmic history, becoming dominant only a few billion years ago. The discovery challenged not only astrophysics but also philosophy, as it forced a reconsideration of the ultimate fate of the cosmos and the mechanisms driving its expansion. By integrating multiple independent observations, including baryon acoustic oscillations and weak gravitational lensing, scientists confirmed that dark energy is the most plausible explanation for the observed acceleration. The revelation of acceleration transformed the universe from a simple expanding cosmos into a complex system dominated by unknown forces, emphasizing that our understanding of space, time, and energy remains incomplete. Even with modern instruments like Hubble, Keck, and the upcoming James Webb Space Telescope, astronomers continue to refine measurements of Type 1a supernova, probing both the past expansion rate and the potential future trajectory of the cosmos. The discovery of dark energy underscores the importance of precise observational techniques, showing how seemingly minor differences in brightness or redshift can reveal fundamental truths about the structure and destiny of the universe. Ultimately, the Type 1a supernova observations revealed that the universe is not only expanding but accelerating, transforming cosmology from a descriptive science into a predictive discipline capable of exploring the ultimate fate of all cosmic structures. Dark energy is an enigmatic force that permeates all of space, pushing galaxies apart and counteracting the attractive pull of gravity. Yet its true nature remains one of the greatest unsolved mysteries in physics. One of the simplest explanations is the cosmological constant, originally proposed by Einstein, which treats dark energy as a fixed, unchanging property of spacetime itself. In this model, the energy density of empty space remains constant, exerting a repulsive effect that grows in influence as the universe expands, gradually dominating over matter and radiation. Quintessence offers an alternative perspective, describing dark energy as a dynamic field that evolves over time, with its properties potentially changing depending on the scale of the cosmos. Unlike the cosmological constant, quintessence allows for variations in the acceleration rate, which could explain subtle differences observed in Type 1a supernova surveys at different distances. Vacuum energy, arising from quantum fluctuations in empty space, provides another theoretical explanation, linking the properties of dark energy to fundamental physics at the smallest scales. These quantum effects predict a small but pervasive energy throughout space, which can drive cosmic acceleration without violating the laws of general relativity. Despite decades of research, no direct detection of dark energy has been made, and its origin continues to challenge our understanding of the universe's composition and evolution. Observations of the cosmic microwave background, baryon acoustic oscillations, and galaxy clustering provide indirect evidence for dark energy, constraining its density and equation of state. The cosmological constant implies an unchanging equation of state, while quintessence models allow for a time-varying parameter, offering a framework to interpret subtle discrepancies in observational data. Astrophysicists also consider the possibility of vacuum energy being linked to the zero-point energy of quantum fields, suggesting a connection between the largest scales of the cosmos and the smallest scales of particle physics. Measuring dark energy precisely remains a priority for missions such as the Dark Energy Survey, the Euclid satellite, and the Nancy Grace Roman Space Telescope, which aim to map cosmic expansion with unprecedented accuracy. The influence of dark energy grows stronger as the universe expands, meaning that in the distant future its repulsive effect could dominate local gravitational interactions, isolating clusters of galaxies from one another. Current observations suggest that dark energy behaves similarly to a cosmological constant, but small deviations could point to new physics beyond the standard lambda CDM model. Type 1a supernovae remain essential tools for probing dark energy, as they allow precise measurement of how the expansion rate has changed over billions of years. Large-scale structure surveys complement supernova studies by mapping the distribution of galaxies and clusters, revealing how cosmic acceleration affects the growth of matter over time. Theoretical physicists explore alternative scenarios, including modified gravity and emergent phenomena, attempting to explain dark energy without invoking an unknown energy component. Even subtle shifts in the equation of state parameter, measured through combinations of CMB, supernovae, and galaxy surveys, could provide clues to whether dark energy is constant or dynamic. Understanding dark energy is critical not only for explaining the current acceleration but also for predicting the long-term fate of the universe, including scenarios like eternal expansion, heat death, or a big rip. By combining observations across multiple wavelengths and using independent techniques, scientists reduce systematic errors, improving confidence in the properties assigned to dark energy. The dynamic interplay between theory and observation continues to refine our models, ensuring that future surveys can distinguish between cosmological constant, quintessence, and other exotic possibilities. Despite its elusive nature, dark energy shapes every scale of the universe, from the acceleration of distant galaxies to the ultimate destiny of cosmic structures. Ongoing research seeks to link dark energy with fundamental physics, potentially revealing connections to string theory, extra dimensions, or modifications of general relativity. In summary, dark energy represents a profound mystery, a force or property that drives cosmic acceleration, challenges our understanding of fundamental physics, and dictates the universe's long-term evolution. Measuring the universe's expansion requires precise observations of both nearby and distant cosmic markers, providing a ladder to determine the rate at which space itself stretches. The Hubble constant quantifies this expansion, expressing how fast galaxies recede per unit of distance, yet its exact value has proven surprisingly contentious. Cepheid variable stars in nearby galaxies serve as fundamental calibrators, their predictable brightness variations enabling astronomers to estimate distances with remarkable precision. By comparing Cepheid distances with Type 1a supernovae in the same galaxies, scientists extend the cosmic distance ladder to far-off regions, bridging local measurements with the large-scale universe. Recent surveys using Hubble Space Telescope data suggest a value for the Hubble constant around 73 km per second per megaparsec, implying a faster expansion than early universe predictions. Conversely, analyses of the cosmic microwave background by the Planck satellite yield a lower Hubble constant near 67 km per second per megaparsec, based on the universe's state 380,000 years after the Big Bang. This discrepancy, known as the Hubble tension, remains one of modern cosmology's most pressing puzzles, hinting at potential new physics or unrecognized systematic errors. Researchers explore multiple explanations for the tension, including modifications to the properties of dark energy, additional relativistic particles, or subtle biases in local distance measurements. Gravitational lensing of distant quasars offers an independent approach to estimate expansion rates, using time delays between multiple light paths to infer the Hubble constant. Masers in galactic nuclei provide another precise method, with microwave emission lines tracing orbital velocities that yield direct geometric distances, bypassing some calibration uncertainties. Combining multiple independent techniques increases confidence in the measured Hubble constant while revealing that the tension is not easily resolved by a single source of error. The implications of differing expansion rates are profound, influencing predictions for the age of the universe, the timing of structure formation, and the interpretation of cosmic acceleration driven by dark energy. Recent efforts include using surface brightness fluctuations of elliptical galaxies as a complementary method, providing yet another independent distance measurement to refine the Hubble constant. Gravitational wave events from merging neutron stars offer a new, standard siren technique, directly connecting the amplitude and frequency of waves to luminosity distance, adding an independent check on expansion rates. The cumulative evidence from multiple approaches underscores that while expansion is well established, the precise value of the Hubble constant continues to challenge theorists and observers alike. Understanding this tension may point toward new phenomena in the early universe, including departures from the standard lambda CDM model or interactions among dark matter and dark energy. As surveys grow in scope and precision, astronomers anticipate further refinement of the local Hubble constant, potentially narrowing the gap with early universe predictions and revealing subtle cosmic effects. The Hubble tension exemplifies how even small uncertainties in measuring cosmic distances propagate into large differences in inferred cosmological parameters, emphasizing the importance of cross-validation. By comparing expansion rates derived from supernovae, Cepheids, masses, gravitational lensing, and gravitational waves, researchers create a robust multi-pronged approach that reduces the likelihood of systematic errors dominating the results. Ultimately, precise measurement of the Hubble constant, not only refines our understanding of the current expansion, but also provides a key benchmark for testing models of dark energy, cosmic acceleration, and the ultimate fate of the universe. The discovery of cosmic acceleration has profound implications for the universe's future, suggesting that the expansion may continue indefinitely without slowing, fundamentally reshaping our expectations for cosmic evolution. If dark energy continues to dominate over gravitational attraction, distant galaxies will drift beyond the observable horizon, leaving local groups isolated in an ever-expanding void. This persistent acceleration implies a cosmos where large-scale structures remain intact locally, but communication or travel between distant regions will eventually become impossible. Understanding these dynamics informs our models of the ultimate fate of the universe, whether through eternal expansion, heat death, or other scenarios driven by the unseen forces shaping cosmic history. Should dark energy remain constant, the most likely fate is a slow approach to thermal equilibrium, a heat death where stars exhaust their fuel, black holes evaporate, and the cosmos fades into an ultra-cold darkness over unimaginable timescales. If instead dark energy grows stronger with time, a big rip scenario could unfold, where galaxies, stars, planets, and even atoms are torn apart as space-time's expansion overwhelms every binding force. A more exotic possibility is vacuum decay, in which a lower energy state of the quantum vacuum nucleates a bubble that expands at near light speed, rewriting the laws of physics as it passes. In contrast, if dark energy were to diminish, gravity might eventually reassert itself, slowing the expansion and hinting at cyclic models that imagine successive epochs of growth and renewal. To distinguish among these futures, cosmologists measure the equation of state parameter W with ever higher precision, searching for any deviation from -1 that would betray evolving physics. Beyond late-time acceleration, clues about the earliest moments arise from inflation, a brief burst of superluminal expansion that smoothed and flattened the young universe. Inflation explains why the cosmos looks nearly identical in all directions, and why space is so close to Euclidean, solving the horizon and flatness puzzles in one sweeping idea. Tiny quantum jitters stretched by inflation became the seeds of structure, leaving a near-scale invariant spectrum of fluctuations imprinted on the cosmic microwave background. Polarization patterns in the CMB, especially the elusive B modes, could reveal primordial gravitational waves, offering a direct probe of inflation's energy scale. Large-scale structure surveys detect baryon acoustic oscillations, fossil ripples of primordial sound that serve as standard rulers to track expansion across cosmic time. During the cosmic dawn in the epoch of Ryanization, the first stars and galaxies ignited, bathing intergalactic hydrogen in ultraviolet light and transforming the foggy universe into a transparent one. James Webb. Space telescope observations are pushing the frontier to earlier eras, revealing surprisingly complex galaxies that challenge timing and efficiency models of formation. Cold dark matter provides the scaffolding for galaxy growth, with halos forming first and baryonic gas cooling within them to ignite stars and build disks, bulges, and clusters. Neutrinos, though nearly massless, subtly smear small-scale structure, letting cosmologists weigh them by how much they suppress clustering on the tiniest measurable scales. Gravitational lensing maps the invisible by tracing how mass warps light, delivering direct measurements of the cosmic matter distribution without relying on galaxy light alone. Weak lensing shear across millions of galaxies constrains the growth rate of structure, cross-checking supernova and CMB inferences about dark energy's influence. 21-centimeter cosmology targets the hyperfine whisper of neutral hydrogen to chart vast volumes through the dark ages, promising a 3D movie of early structure formation. Standard sirens from gravitational wave mergers offer distance measurements independent of light, enabling new calibrations of the Hubble constant and tests of gravity over cosmic scales. Cross-correlations between galaxy maps, lensing, CMB, and 21 cm surveys knit a tighter cosmic web, reducing systematics and revealing consistent physics across methods. On the smallest scales, feedback from supernovae and black hole wind stirs and heats gas, regulating star formation and shaping the observable fingerprints of galaxy evolution. Chemical enrichment spreads the ashes of stars through space, with elements forged in cores and kilonovae becoming the raw material for planets, life, and new generations of suns. Black holes grow by accretion and mergers, lighting quasars that beacon across the universe and trace the co-evolution of galaxies and their central engines. Cosmic voids, vast regions nearly empty of matter, act as clean laboratories for expansion physics, their gentle flows complementing the crowded signals from clusters. Precision tests of gravity compare general relativity's predictions with cosmic data, hunting for tiny deviations that could hint at modified theories on the larger scales. Future missions like Euclid and the Roman Space Telescope are designed to map billions of galaxies, tightening constraints on dark energy's behavior and the geometry of space-time. As measurements sharpen, the Hubble tension remains a lodestar, motivating new techniques and deeper scrutiny of calibrations, sample selection, and early universe physics. Whatever the precise path ahead, the narrative of expansion links first light to final fate, binding quantum fluctuations to clusters and horizons in a single evolving tapestry. In this unfolding story, every photon, ripple, and shadowed void adds a line of evidence, reminding us that the universe is both our laboratory and our legacy among the stars. Possible fates of the universe opens with the quiet path, a future where expansion steadily dilutes structure until activity wanes and the cosmos settles toward stillness. In this scenario, the cosmic horizon swells with time, pushing distant galaxies beyond reach so that their last photons fade into wavelengths too long to ever be seen again. As isolation deepens, only our local collection of galaxies remains gravitationally bound, merging over vast ages into a single star city, adrift in an ever emptier expanse. With fresh gas exhausted or warmed beyond the ability to condense, the birth of new stars dwindles, and the remaining stellar populations age toward a universe ruled by embers rather than flames. Massive stars end quickly in brilliant outbursts, while modest suns endure for longer spans, but all paths converge on remnants that no longer fuse and only give back stored heat. White dwarfs cool and crystallize, their lattices locking in energy as they radiate away the last warmth, on track to become black dwarfs that are dark to every eye. Neutron stars persist as ultra-compact husks, rarely colliding in lonely encounters that send brief flashes into an otherwise dim sky before silence returns. Brown dwarfs and rogue planets drift through the dark, shedding heat slowly until their surfaces approach the temperature of the background and no longer shine. Black holes dominate the deep future as the final engines of gravity, swallowing strays and stirring the last bound systems until even those reservoirs are spent. Over unimaginable spans, they themselves leak energy through quantum effects, releasing a trickle of radiation that ends in a final burst and leaves only faint particles behind. As light thins and temperatures fall, the cosmic microwave background stretches to wavelengths larger than any practical detector, and the sky becomes a canvas without features. If protons endure, matter remains as cold relics for stupendous ages. If they decay, atoms gently disassemble, hastening the slide toward a thin bath of radiation and light particles. Gravitational encounters slowly unbind what little remains, ejecting remnants into the dark or feeding the last compact objects, while internal motions wind down toward equilibrium. At last, the universe approaches maximum entropy, a quiet sea near absolute zero where change is rare and information lies spread thin across an ever-expanding stage. In the Big Rip picture, dark energy does not merely sustain expansion, it intensifies with time so that its density rises as the universe grows, turning the cosmic stretch into a runaway process that ends after a finite interval rather than in endless dilution. Physically, this corresponds to an equation of state with W less than -1, often called phantom energy, where the pressure is so negative that it overwhelms every other influence and drives the scale factor to diverge at a definite moment. As the expansion rate swells, the Hubble radius, the distance over which causal contact can be maintained, shrinks, meaning that regions once communicative are cut off, and the sky evacuates familiar structures long before disintegration begins. The sequence of unbinding proceeds from the largest associations downward. Superclusters first lose coherence, then clusters disperse, and galaxies themselves no longer hold their stars as the repulsive effect outpaces the deepest gravitational wells. Once galactic potentials fail, stellar neighborhoods unravel, orbits elongate and dissolve, and long stable architectures like spiral disks and bulges smear into streams that no longer complete closed paths around a common center. Local systems yield next. Planetary arrangements and asteroid bands are stripped as the accelerated expansion inserts a steadily growing tidal field, turning once secure ellipses into trajectories that drift apart irreversibly. Even compact binaries cannot shelter indefinitely. The stretching background adds energy to their binding faster than gravitational radiation can drain it, so separations increase despite their mutual pull, a reversal of ordinary expectations. As the critical time approaches, forces that hold matter together are challenged. Molecular bonds feel a uniform strain, lattices fracture, and materials lose coherence not from heat or impact, but from the inexorable growth of the cosmic scale. Eventually, electromagnetic binding yields, atoms no longer keep electrons in place, spectra cease to have lines in the traditional sense, and the concept of a stable chemical species evaporates into a bath of charged constituents. Deeper still, the same logic threatens the strong forces confinement scale. Nuclei can no longer resist the externally imposed expansion, and hadronic structure unravels as the timeline approaches its terminal singular behavior. Black holes, which would dominate other far futures, meet a different fate here. The surrounding space-time accelerates so violently that horizons are overrun. Accretion disks disperse and the objects themselves cannot remain intact against the tide. From a thermodynamic perspective, the Big Rip cancels the long asymptotic slide toward equilibrium. Entropy accounting becomes dominated by the singular end state rather than by slow cooling, replacing gradual fading with an abrupt terminus. Mathematically, the scale factor follows a power law that diverges at a finite cosmic time, and observable intervals between milestones compress. Billions of years to unbind clusters, millions to disrupt galaxies, then mere years to erase planetary systems. Closer to the finale, days or minutes separate the loss of molecular cohesion from atomic failure, so that any remaining structures, biological, geological, engineered, transition almost instantaneously from integrity to dispersal. Causality itself becomes local to the point of meaninglessness. As the horizon contracts, no signal can coordinate action across even modest distances, and the universe fragments into innumerable regions that cannot share information. Observationally, the telltale is W persistently below -1, with distance redshift relations and growth of structure trends deviating from the cosmological constant case in a way that cannot be absorbed by calibration tweaks alone. If future surveys tighten constraints to reveal genuine phantom behavior, forecasting the remaining time becomes possible. One could estimate when clusters dissolve, when galaxies lose stars, when systems like ours disassemble, and when matter itself fails. Yet the path to such a verdict is narrow. Systematic uncertainties, selection effects, and cross-correlations among probes must be tamed to ensure that an apparent W below -1 is not a mirage produced by bias or modeling limits. Alternative explanations, modified gravity, interactions in the dark sector, or evolving fields with temporary effective W below -1, could mimic phantom signatures without culminating in a terminal rip. If, however, the cosmos truly follows a phantom trajectory, the narrative closes not by cooling but by catastrophic separation, where space accelerates beyond any capacity for binding and every level of organization yields in a crescendo toward the final instant. In that last heartbeat of cosmic time, the metric that once knit galaxies and atoms together ceases to support connection, and all that remains of structure is the memory encoded in the equations that predicted its undoing. The Big Rip thus stands as the sharpest counterpoint to gentle endings, not a dimming candle but a universe-wide acceleration that intensifies until geometry itself denies cohesion, closing the book in a flash rather than a whisper. A different path from the tearing future is a turning future, where the agent driving acceleration weakens, the deceleration parameter changes sign, and the same Friedman equations that once favored expansion permit a halt and reversal. If dark energy is not a true constant but an evolving field whose energy density falls or becomes negative, cosmic acceleration can give way to slowing growth, then to a maximum scale, and finally to contraction. In models with slight positive curvature or sufficient effective matter density, once the repulsive term fades, gravity can overcome expansion and pull large-scale structure back together toward a global recollapse. As contraction begins, the background radiation temperature rises with the scale factor's decline, the CMB blue shifts, and the dark night slowly brightens in long wavelengths before heating the full spectrum. Gas compressed by shrinking volume shocks and heats, galaxy interactions accelerate, and black holes at the centers emerge, systems flare as inflows intensify under the deepening potential wells. On approach to high density, anisotropies can grow and mix, with chaotic gravitational behavior described in BKL analyses, hinting that homogeneous contraction may fragment into increasingly complex local dynamics. Classically, general relativity admits a terminal singularity where curvature diverges, but near that regime, quantum gravity effects are expected to intervene, making the final moments a question for new physics. Observationally, current data favor near-flat geometry, and an equation of state close to -1, so a crunch is disfavored today, yet time-varying W or interactions in the dark sector could still redirect the long-term trajectory. Mechanisms that enable reversal include scalar fields rolling into negative potentials, K-essence with non-standard kinetic terms, or couplings that transfer energy between dark matter and dark energy. In ekpyrotic scenarios, a slow, ultra-stiff contraction smooths and flattens space before a transition to expansion, replacing a singular end with a controlled approach that can seed observed large-scale structure. Loop quantum cosmology proposes that space-time discreteness generates a repulsive effect at Planckian density, turning a classical crunch into a bounce that bridges a prior universe to ours. Conformal cyclic cosmology envisions aeons linked by a boundary where all massive particles fade and the geometry can be rescaled, allowing a new expansion to follow an ultra-dilute long-term future. Other late-time possibilities avoid both singularities and bounces. In a little rip, the acceleration grows without a finite time end, but eventually unbinds systems, while a pseudo-rip stalls short of disrupting everything. Phase transitions in a dark sector, vacuum metamorphoses, could switch the cosmic equation of state, converting repulsion into attraction and triggering contraction after an extended era of acceleration. Future precision maps of expansion, history, and growth, combining supernova, baryon acoustic oscillations, weak lensing, and redshift space distortions, will test whether W truly evolves and whether curvature or interactions nudge the universe toward turnaround. Large spectroscopic surveys and next-generation CMB experiments can track subtle departures from a cosmological constant, while galaxy clusters and void flows provide independent checks on any emerging trend toward recollapse. If evidence someday points to a contracting phase, the sequence would invert the long thermal drift, rising background temperature, accelerated mergers, radiation domination, and a final approach governed by quantum corrections rather than classical collapse. Against that backdrop, exotic proposals share a common lesson. The universe's fate hinges on the microphysics behind cosmic acceleration, and only by pinning down how energy and geometry co-evolve can we discriminate between a quiet fade, a catastrophic end, a rebirth, or a return to contraction. In the family of exotic endings and beginnings, the Big Bounce reframes the deepest moment of compression not as a wall but as a bridge, replacing a terminal singularity with a finite minimum size where gravity's usual pull is offset by new microphysics, and the scale factor reverses from shrinking to growing. One route to a bounce invokes quantum corrections that make space-time effectively repulsive at extreme density, capping curvature and pressure so that collapse cannot proceed unchecked, while another uses ultra-stiff ingredients that drain away irregularities and prepare smooth initial conditions for the next round of expansion. Thermodynamics demands care in any cyclic story, so modern bounce models build in entropy management, long eras of accelerated dilution to thin out relics, asymmetric contraction phases that radiate excess heat, or mechanisms that reset degrees of freedom so each cycle can begin without inherited clutter. Matter bounce frameworks flip the usual sequence by letting structure seeds grow during contraction, producing nearly scale-free imprints that survive the reversal and reappear as the density ripples we later map in galaxies and the background glow, thereby turning yesterday's approach into tomorrow's scaffolding. Near the minimum, exotic stresses prevent horizons from forming and keep causal patches in touch, so the new expansion can emerge coherent rather than patchwork. After the rebound, reheating repopulates particles and light, and chemistry eventually resumes on a canvas that remembers its pre-bounce choreography. Tests for a bounce aim at signatures beyond simple temperature patterns, specific non-Gaussian shapes in the primordial fluctuations, faint gravitational wave backgrounds with distinctive spectra, or tiny departures from flat geometry that a future survey might catch if the universe carries even a whisper of pre-bounce curvature. While bounces rewrite the past-future junction, eternal inflation multiplies the stage, proposing that inflation does not end everywhere at once but continues in remote regions, spawning a patchwork of pocket universes as quantum jitters push some zones to keep inflating, while others exit and ignite hot big bangs. Each pocket cools into its own cosmic history, with potentially different effective constants or particle content, set by the vacuum it lands in and the path it took through the landscape. So diversity of worlds is not an embellishment but the natural outcome of inflating space that never fully shuts off. Where bubbles meet, their boundaries can leave subtle scars, circular temperature modulations in the background glow, correlated polarization rings, or low variance patches that would betray an ancient encounter across the sky, observational breadcrumbs that surveys can hunt without assuming we are alone in our cosmic neighborhood. Another generic relic of eternal growth is negative spatial curvature on very large scales, a geometric echo of exiting inflation late, improved distance ladders, precise standard rulers, and lensing maps can tighten the net around any small curvature that still lingers in our observable patch. Beyond direct imprints, multiverse logic reshapes inference. If different pockets support varied conditions, selection effects matter, and probabilities must weigh not only dynamics but the abundance of observers they permit, turning the measure problem into a central task for making crisp predictions rather than broad plausibility claims. Despite the philosophical heft, tests remain concrete. Search for bubble collision templates, push polarization sensitivity to catch primordial swirls, compare structure growth against inflationary expectations across redshifts, and watch for any stable anomalies that resist instrumental or astrophysical explanations, and point to physics beyond a single cosmos script. If both avenues prove fruitful, a hybrid vista emerges, an eternally sprouting background where bounces reset individual pockets after crunch-like contractions, or where rare regions cycle while others drift forever, making cosmic cartography as much about when we live as about where we look. In all such models, the unifying theme is modesty before the data. Follow the equations beyond familiar domains, identify clean observational stakes in the ground, and let future measurements decide whether our horizon marks an ending, a doorway, or just one tile in a sprawling, ever-creating mosaic. Humanity's place in an expanding cosmos begins at home, where the grand drama of expansion meets the local choreography of gravity, and the Milky Way's destiny is shaped less by the outward stretch of space than by nearby partners drawing us into a shared future. For all the distant galaxies that recede into dimmer hues, the Andromeda Galaxy approaches on a slow, majestic collision course, its motion dominated by mutual attraction that easily overrules the gentle push of the universe's growth at our small scale. This convergence is not a catastrophe but a restructuring of star systems. Over billions of years, tidal forces will warp disks, fling long streams of stars into arcs, and funnel gas toward the centers where fresh bursts of star formation ignite. Because stars are tiny compared with the gulfs between them, direct stellar collisions will be rare. The drama plays out in orbits and clouds, with trajectories reshuffled while most suns and their planets pass unharmed through changing gravitational landscapes. As the galaxies interpenetrate, the night sky of a patient observer would swell with intricate veils of light. Andromeda's spiral will first widen to a luminous smear, then to a tangled lattice as our own disk distorts and knots of young stars sparkle in tidal bridges. Central black holes, one in the Milky Way and one in Andromeda, will spiral inward through a sea of stars and dark matter, their friction with the background gradually tightening a binary that ultimately coalesces in a brief crescendo of gravitational waves. Each pass of the galactic cores will shake loose gas and dust, driving outflows but also compressing clouds. The balance between heating and cooling and the availability of metal-rich material will determine whether the merger triggers a long starburst or a quicker blaze followed by quiescence. When the dance settles, the remnant, often nicknamed Milk Dromeda, will be a more rounded, massive galaxy with a thickened core, extended halo, and a stellar population combining the histories of two great spirals and a retinue of satellites, streams, and shells. Our Sun, by then older and drifting on a new orbit, will likely reside far from the central maelstrom, its path altered by gentle nudges from passing masses rather than any singular upheaval. The solar system's fate is statistical, not predetermined by a single close encounter. While expansion sets the far-field stage, the local group remains a gravitationally bound island, its core members, the Milky Way, Andromeda, and Triangulum, woven together by a shared halo of dark matter that anchors their long-term evolution despite the universe's overall drift. Outside this island, expansion does its quiet work. Over immense durations, the luminous archipelago of nearby groups will thin from view, leaving our merged galaxy and its companions as a self-contained laboratory of stars, clusters, and gas that orbit a common center of mass. The notion of island here is literal in cosmological terms. Communication, trade of matter, and exchange of light with faraway galaxies gradually ceases as wavelengths stretch and horizons shift, not because space stops, but because signals cannot keep pace with the enlarging separation. Within this island, dynamics grow richer. Dwarf galaxies are tidally stripped, forming filigrees that trace their orbits like ink in water, while globular clusters migrate and sometimes dissolve, sprinkling aged stars into the halo and thickening the stellar soup between larger members. Gas reservoirs determine the cadence of future starbirth. If merger-driven inflows preserve enough cool material, the remnant may sustain star formation episodes, but feedback from supernovae in the active nucleus can heat or expel gas, regulating the long arc of stellar renewal. Humanity's place in this story is not only to watch but to model, to compare simulations against stellar streams and halo substructures, reading the fossil record of past encounters to forecast the tracks of the coming union with ever sharper precision. Already measurements of proper motions and distances let astronomers reconstruct the three-dimensional ballet. As data improve, refined orbits for satellites and the central trio will narrow the range of possible timetables for first approach, interpenetration, and final coalescence. In the nearer term, tidal stretching around both galaxies continues to feed long, faint structures. Mapping these wisps offers a stress test for mass models of the shared halo and for the distribution of unseen matter that sculpts the overall potential. At the scale of star systems, the merger's most common effect is dynamical heating, gentle changes in orbital energy and inclination as passing masses perturb trajectories. Some stars are flung into the halo, others sink inward, while most simply trade a quiet suburb for another. Future skies inside the remnant could be richer in contrast than today's. Dust lanes, star-forming knots, and diffuse plumes will thread the firmament, and the central region may shine with intermittent activity as the black hole accretes fresh material in luminous episodes. For civilizations charting calendars over geological timescales, the approach of Andromeda offers new reference points, moving constellations stamped by external stars, shifting standard candles, and a slowly evolving parallax baseline that lengthens with the system's changing geometry. The local group's boundedness reshapes cosmological practice. While distant beacons dim beyond recovery, internal standards remain available, Cepheids, eclipsing binaries, surface brightness ripples, allowing precision distance work and tests of gravity within the island long after the outer ocean fades. Deep-time astronomers will do cosmology as naturalists do fieldwork, by cataloguing streams, reconstructing ancient mergers, weighing halos with lensing of nearby arcs, and listening for the low hum of black hole binaries with detectors tuned to the remnant's own gravitational choir. Even the fading of external galaxies does not erase the memory of the wider universe. Background radiation persists, albeit stretched to longer wavelengths, preserving a spectral relic that encodes conditions from early times and sets absolute reference scales for temperature and expansion history. Human narratives will likely entwine with this astronomical evolution. Myths recast as science changes the night sky, art and philosophy reframed by closer vistas, and practical navigation updated to reflect a firmament where familiar guide stars drift while a new crown rises in the north. Technology situates our species as participant observers. Radio maps of neutral hydrogen can track inflows, infrared surveys can pierce dust to reveal hidden star nurseries, and time-domain instruments can follow tidal supernovae and transient flares as orbits shear clouds into luminous knots. As the remnant matures, chemical evolution continues. Each generation of stars enriches its surroundings with heavier elements, and the merged galaxy's metallicity field bears the imprint of where gas funneled, stalled, or was blown clear during the upheaval. Planetary prospects follow chemistry. Star-forming rings stirred by the merger may host metal-rich disks where rocky worlds are more probable, while other zones grow quiescent, leaving their ancient systems to drift as quiet witnesses of earlier epochs. The bound island's long-term stability does not preclude change. Satellite dwarfs will continue to rain inward, their stars painting new streams, their dark halos massaging the potential, and their gas, if any remains, briefly rekindling local star formation before it's consumed or expelled. Triangulum's role may be that of a recurring perturber, whether it merges directly, dances in resonant passes, or is stripped to a core before sinking. Its influence will leave asymmetries that future sky maps can decode into a history of repeated tides. Gravitational waves offer the clearest punctuation marks in this saga. The final union of central black holes will send ripples across the island detectable by distant instruments if they share our epoch, or at least by local detectors when our remnant culture listens with tuned basslines. For beings bound to the remnant, the concept of universe tightens to what can be measured, yet the logic of physics preserves the insight that beyond the island lies an ocean once visible, its imprint carried by background light and by the very structure of the laws that shaped our merger. Education and memory become instruments as vital as telescopes. Star atlases must annotate movement, long-range projects must plan for shifting beacons, and cultural archives will preserve how the sky looked when two great spirals were still separate across a quiet gulf. The energy budget guiding this tale remains straightforward. Within the local group, potentials dominate. Beyond it, the expansion accelerates. The interplay insulates our island, allowing an entire cosmic history to unfold locally, even as the outer stage recedes from the playhouse. As Milkdromeda ages, stellar populations shift toward redder hues, while hot young clusters punctuate the outskirts where late infall and cloud collision spark new light. The color map of the remnant becomes a fossil of its layered assembly. Navigation for future explorers will lean on pulsars, quasars within the island, and artificial beacons, replacing today's extragalactic references with a network woven inside the remnant's own framework of stable clocks and calibrated distances. Even as horizons narrow, curiosity widens. The local group's laboratory holds questions spanning turbulence in cold gas, feedback coupling in starbursts, the microphysics of dust growth, and the mapping of dark subhalos through their stirring of stellar streams. The merger refines our understanding of habitability at galactic scales. Radiation fields, supernova rates, and cloud densities reorganize, creating neighborhoods that wax or wane in potential for stable, long-lived biospheres under evolving stellar weather. Future chronologies may be written in rings of star formation, not unlike tree rings. By reading ages across the remnant's disk and halo, historians of the sky will tie cultural eras to cosmic episodes. First approach, tidal bloom, coalescent calm, without ever leaving the island. The local group's bound nature also preserves rare archives, ancient star clusters, hypervelocity runaways from close interactions, and long-lived binaries that carry imprints of the gravitational fields they traversed, each a document in the library of Milkdromeda. Cosmic rays and magnetic fields trace the merger's afterglow. As gas shocks and outflows thread the halo, tangled fields guide particles into arcs that radio telescopes can paint, revealing where energy leaked from the central furnace into the wider atmosphere. If curiosity leads us outward, the island's periphery remains a frontier. The faintest streams and the coldest gas clouds at the edge probe the transition from bound to barely bound, hinting at where the remnant's influence yields to the slow tide beyond. Against this evolving backdrop, humanity's place is both tenuous and empowered. We are small within the remnant, yet capable of measuring, modeling, and remembering enough to knit a coherent story from first sight of Andromeda to the settled quiet of a merged sky. That story, told through instruments and ideas, reframes expansion as context rather than destiny at our scale. Space grows in the distance, but here, gravity writes the next chapters, and the local group's island becomes the stage on which our descendants will read the cosmos. In sum, what expansion means for the Milky Way is twofold: an outward silence growing beyond the island, and an inward symphony of tides, mergers, and renewal that culminates in Milkdromeda, a single enduring city of stars where the universe's grand motion and local gravity meet. The eventual collision with Andromeda is therefore less an ending than a renovation. Our home galaxy will trade spiral grace for composite grandeur, and the local group will settle into a bound, self-sufficient world whose changing sky continues to teach long after distant fires dim. And as the archipelago of neighbors fades, the local group as a gravitationally bound island becomes not a limit, but a promise. a laboratory big enough for deep questions, close enough for detailed answers, and stable enough to hold memory as we learn to read the remnants light. Far ahead in time, the visible universe shrinks in practice even as space itself grows, because light from remote systems dilates, dims, and slides to wavelengths that no instrument can collect, turning cosmology into a study of what remains inside our reachable laboratory, rather than what lies beyond it. The physics of fading is precise. Surface brightness drops with the fourth power of 1 Plz. So identical galaxies look not just farther, but intrinsically fainter per unit area, a Tolman dimming that eventually defeats any finite telescope and leaves the deep sky starved of detail. Spectral lines that once anchored distance measures drift beyond favored bands. Hydrogen's Lyman alpha migrates past infrared, dust thermal bumps crawl to microwave, and the familiar ladder of features for redshift fitting collapses as the universe's expansion stretches every photon budget thin. Even before total invisibility, time dilation slows the cosmic clock of distant events. Supernova light curves lengthen by 1 Plz. Quasar flickers smear into languid variations, and the cadence of the high redshift sky grows lethargic, challenging surveys to wait longer for each transient's full story. Real-time cosmology offers another preview of vanishing. The Sandage Lobe redshift drift, a tiny change in spectral lines over decades, directly reveals whether expansion speeds up or slows, but the signal, centimeters per second per year, demands exquisite spectrographs and stable stars to track. As expansion runs on, the cosmic event horizon defines a limit to what can ever influence us. Galaxies beyond that boundary remain forever causally disconnected, their photons always a step too late, so the observable map becomes a fossil embedded in our local spacetime. Gravitational lensing will be the last canvas to fade. Massive halos in our neighborhood continue to bend and magnify background light, carving arcs and rings that persist while sources remain visible. But the arc field thins as distant beacons redshift out of sight. Not all messengers vanish equally. Neutrinos stream with only weak interactions, and gravitational waves pass unimpeded by matter, yet both redshift as the scale factor grows, pushing them to energies and frequencies so low that detectors must grow more sensitive than any device yet built. The cosmic microwave background continues its long chill, its temperature falling as 1 AT, and its peak sliding to meter scales. Eventually, the glow becomes indistinguishable from local noise unless receivers are cooled, screened, and tuned to wavelengths that today we would call radio. Far ahead, the dominant backgrounds may be gravitational and neutrino in character, a faint hum from countless black hole mergers and a thin sea of relic neutrinos that encode the earliest thermodynamic chapters, leaving particle detectors and interferometers as the last windows on the wider past. Against this long view, the nearby universe grows in contrast. While remote clusters fade, tidal streams, dwarf remnants, and halo substructures inside our gravitational island sharpen as targets, turning the late cosmos into an archival workshop rather than a panoramic survey. Future astronomers will pivot from breadth to depth, reconstructing assembly histories from stellar chemistry, mapping dark subhalos via stream perturbations, and watching the slow secular drift of local galaxies across millennia to weigh the island's mass with exquisite astrometry. Even communication follows the physics of visibility. Interstellar networks will depend on relay architectures confined to bound structures, because intergroup links fade under redshift and noise, making cosmological exchange a relic of earlier times when the sky was richer with extragalactic beacons. The vanishing of distant light does not erase knowledge. Archives of spectra, lens catalogues, and standard candle curves persist, anchoring theories to data gathered while the horizon was generous, and simulations inherit these constraints to forecast dynamics long after direct sightings cease. In the nearer future, visibility declines gradually rather than abruptly, Progressively higher redshift windows require increasingly specialized detectors, deeper integrations, and clever stacking of faint signals, pushing observational technique to its limits as the sky slips away in slow motion. That slow fade makes today's measurements all the more urgent. Every photon recorded now from extreme distances becomes a time capsule for descendants who may read only local signatures, reminding us that cosmology is as much stewardship of data as it is discovery. To study expansion today, humanity relies on a network of instruments tuned to complementary regimes, with space telescopes piercing the infrared fog of early epochs, and ground observatories mapping the statistical texture of galaxies, lensing, and transients across the accessible sky. The James Webb Space Telescope serves as our flagship for the dim and distant. NIRCam reaches deep in the near-infrared to capture first-light candidates. NIR-SPEC's microshutter array isolates dozens of faint targets for simultaneous spectroscopy. And MIRI opens the mid-infrared where dust reprocess starlight and cool gas glow. Webb's prism and grisms turn feeble smudges into redshifts, metallicities, and ionization states, letting us chart ionization's patchwork. Estimate stellar ages only a few 100 million years after the Big Bang, and test whether early galaxies grew through smooth inflow, bursts, or mergers. Calibration is everything in this faint frontier. Absolute spectrophotometry, careful background subtraction, and cross-checks with lensing magnification ensure that number counts, luminosity functions, and star formation histories remain robust against the tricks of noise and selection. While Webb sketches the early canvas, the Vera Rubin Observatory prepares to film the changing sky. Its wide, fast, deep survey will image the southern heavens every few nights, creating a time-lapse of billions of sources where variable stars, supernovae, and microlensing events write the expansion history in light curves. Rubin's difference imaging pipeline will detect and classify transients in near real time, opening a floodgate for spectroscopic follow-up and standard candles at unmatched scale, while its weak lensing shear maps will chart the growth of structure and test gravity across redshift slices. Photometric redshifts turn Rubin's colors into distance estimates. Machine learning models trained on spectroscopic samples will minimize biases and produce tomographic bins for lensing and clustering analyses, converting one observatory's images into a three-dimensional map of cosmic matter. Euclid adds space-based stability to the lensing enterprise. With crisp shapes and slitless spectra, it will cross-link with Rubin to reduce systematics and refine baryon acoustic oscillation measurements, sharpening our ruler for the expansion history back to intermediate redshifts. The Nancy Grace Roman Space Telescope extends this reach with wide-field infrared imaging and spectroscopy. Its microlensing survey will inventory free-floating planets, while its supernova program will trace the Hubble diagram into the red, testing dark energy's equation of state with homogeneous calibrations. Beyond photons, standard sirens promise distances without cosmic ladders. Gravitational wave observatories triangulate mergers, and with a redshift from any counterpart or statistical host identification, they deliver absolute luminosity distances, anchoring expansion with independent physics. Ground detectors catch stellar mass binaries, while the laser interferometer space antenna will target supermassive inspirals, providing sirens that probe deeper into the expansion history and test whether gravity's propagation matches light across cosmological baselines. Meanwhile, radio arrays turn neutral hydrogen into a cosmic backlight. 21 centimeter intensity mapping measures aggregate emission from many galaxies at once, tracing large-scale structure without individually resolving sources and delivering baryon acoustic oscillations with remarkable efficiency. The square kilometer array will push this frontier, charting the cosmic web across redshift ranges that challenge optical surveys, cross-correlating with lensing and galaxy catalogs to cancel systematics, and catching the late-time imprint of expansion on the growth of matter. Fast radio bursts add an unconventional ruler. Their dispersion measures record the electron content along the line of sight, turning a galaxy-scale blink into a probe of the cosmic baryon budget, and potentially a distance indicator when combined with the host identifications. Cosmic chronometers provide yet another angle. Differential age dating of passively evolving galaxies yields dz/dt directly, allowing an expansion rate estimate free of standard candles and rulers, provided stellar population models and metallicities are carefully controlled. On the microwave stage, next-generation experiments will map the Sunyaev-Zeldovich effects, thermal and kinetic, across thousands of clusters, using them to weigh the baryon content, calibrate mass-observable relations, and tease out velocity fields that encode the growth history. CMB polarization missions such as LightBird and ground-based arrays extend the legacy. They seek the faint B-mode pattern from primordial gravitational waves, tighten the optical depth to rionization, and sharpen lensing reconstructions that cross-check structure growth inferred from galaxies. Spectral cartographers like SphereX will survey the whole sky in low-resolution infrared spectra, building a census of emission lines and continua that fill gaps between deep pencil beams and wide shallow maps, enabling uniform studies of star formation and dust across cosmic time. On the ground, multiplex spectrographs, DAISY today and successors tomorrow, harvest redshifts by the millions, delivering precision baryon acoustic oscillations and redshift space distortions that pin down the growth rate parameter FS8, testing whether matter's clumping follows general relativity. Weak lensing systematics attained with meta-calibration, image simulations, and shape measurement ensembles that beat down biases to parts per thousand, converting subtle shears into crisp maps of the projected mass over cosmic time. Forward modeling rises as a unifying method. Rather than correcting data to an ideal, analysts generate synthetic skies from physical parameters, pass them through virtual instruments, and compare to observations, embracing complexity while preserving a transparent path from theory to measurement. Laser frequency combs stabilize spectrographs for redshift drift and precise radial velocities, while adaptive optics and diffraction-limited imaging on giant telescopes resolve crowded fields and sharpen lensing arcs, pushing every photon into a tighter constraint on expansion. Atomic clocks knit precision metrology into astrophysics. Arrays of optical lattice clocks can test gravitational redshift over continental baselines and monitor potential drifts in fundamental constants, linking laboratory time to cosmic time with parts per quintillion stability. Data stewardship becomes its own instrument. Open archives, cross-survey calibrations, and reproducible pipelines ensure that distance ladders, standard sirens, and background maps remain intercomparable, preventing subtle drifts in 0 points from masquerading as new physics. Machine learning assists but does not replace inference. Classifiers triage transients, emulators accelerate parameter estimation, and generative models produce mock skies for training, all while uncertainty quantification guards against overconfidence in patterns coaxed from noise. Cross-correlation is a cosmologist's lie detector, aligning galaxy maps with CMB lensing, 21 cm fields with optical density, or FRB dispersion with large-scale structure, reveals shared physics and cancels survey-specific errors, turning independent views into a coherent whole. The interleaving of methods secures expansion story. Baryon acoustic oscillations fix the ruler. Supernovae trace the candle power, lensing maps the mass, sirens stake out absolute distances, and chronometers check the clock, leaving fewer cracks where systematics can hide. In the time domain, coordinated networks catch rare calibrators. Strongly lensed supernovae with measurable time delays, repeating far-Bs that probe changing electron columns, and tidal disruption events that act as bright, standardized flashes in otherwise quiescent galaxies. Solar system experiments anchor the theory's foundations. Radio tracking of spacecraft, planetary ephemerids, and pulsar timing arrays weave together to test gravity's parameters locally and on kiloparsec scales, ensuring the cosmological model rests on a law that passes every near-field trial. Looking forward, hybrid facilities blur boundaries, telescopes with built-in spectrophotometry, interferometers piggybacking on communication arrays, and constellations of small satellites that tile the sky with coordinated cadence make observing a choreography rather than a set of independent solos. Education and access reshape the workforce that reads expansion. Cloud-based analysis brings petabyte surveys to classrooms, citizen scientists vet lens candidates and transient alerts, and international consortia align standards so discoveries flow where talent appears, not only where hardware sits. Laboratories on Earth mirror the cosmos in miniature. Fluid analogues of horizons, metamaterials that bend waves like gravity, and tabletop quantum simulators of field dynamics let theorists test ideas about expansion and dark energy without waiting for the sky to cooperate. Theories evolve in step. Parameterized frameworks for the equation of state WZ, effective field theories for cosmic acceleration, and modified gravity models with screening mechanisms are benchmarked against joint data sets, with Bayesian model comparison rewarding parsimony and penalizing Baroque fits. As methods diversify, the cosmic triangle, when geometry from distances, growth from clustering, and dynamics from expansions, closes with redundancy. If two corners agree and one deviates, the mismatch points to new physics or hidden errors, a triangulation that keeps the field honest. Today's instruments already glimpse tomorrow's invisibility. Webb's earliest galaxies hint at rapid assembly. Rubin's alert stream drills the practice of catching fleeting signals, and pathfinders for 21-centimeter mapping rehearse techniques that will one day be the only way to read the outer web. Future missions will add missing pieces: Roman's uniformly calibrated supernova ladder, Euclid's stable shapes from space, Lisa's roaring sirens from massive black hole unions, the SKA's tomography of hydrogen scaffolding, and polarization satellites that extract ionization's exact timing. Together, these tools ensure that the narrative of expansion remains testable at many levels. Should dark energy drift, modified gravity leak into lensing, or neutrino mass quietly suppress small-scale power, the combined apparatus will see the fingerprints from multiple angles. And as distant galaxies gradually fade from view over billions of years, the field's center of gravity shifts from discovery to memory, from horizon chasing to island cartography, with instruments repurposed to read the local record as carefully as earlier generations read the sky's far edge. By then, the story of future visibility will be a paradox. The universe grows emptier to our eyes while our models grow richer, because the last pages of observational cosmology are written not in panoramic vistas, but in the subtle grammar of nearby structures shaped by the very expansion that hid the rest. In the present moment, humanity stands at the overlap, able to see both the formative past with Webb's infrared lens and the kinetic present with Rubin's time-lapse, while future missions stitch these views into a coherent atlas that can be reread long after the far shores have gone dark. This is why cosmology prizes redundancy, calibration, and open archives. When the visible frontier closes, what remains is the integrity of methods and the continuity of knowledge, so that the expansion we will one day infer from local fossils agrees with the expansion we measure today in light. In sum, the future visibility of the universe narrows inexorably, but our capacity to study expansion widens as techniques multiply. From Webb to Rubin to Roman and beyond, from sirens to 21 centimeters to polarization swirls, we are building a self-checking toolkit that reads the cosmos from multiple alphabets at once. And if billions of years hence those alphabets speak only of the local group's island, they will still carry the syntax of universal law. Every local stream, lens, clock, and wave will pass into the same expansion grammar, ensuring the story of a growing cosmos remains legible even as its distant letters fade. Philosophical reflection begins with the ordinary. a mind on a small world noticing that the night sky is not a ceiling but a process, and that meaning must be coined inside a universe whose long arithmetic trends toward thinness and quiet. The prospect of eventual silence does not nullify value, it reframes it as something locally assembled from finite gradients, sunlight, chemistry, curiosity, rather than bestowed from an infinite stage, putting responsibility squarely on living agents to author significance. Thermodynamics enters ethics by way of constraint. Life is a dissipative structure that rides free energy downhill while building temporary islands of order. Duty, then, is not to fight entropy in the abstract, but to convert available work into durable knowledge and kindness before the gradient fades. Information theory turns this into math. Bits stored in brains, books, and chips cost energy to write and to safeguard. Landauer's principle tells us erasing a bit releases heat, reminding us that memory is thermodynamically expensive and therefore precious. From this lens, culture is a cooling strategy for ignorance. Error-correcting institutions, peer review, replication, open archives act as conceptual cryogenics, slowing the loss of fragile insights to noise and time. A finite future also sharpens moral circles. If horizons contract, the beings we can help will almost certainly share our island of gravity, making neighborliness not a sentiment but an astrophysical fact about where aid can travel and return. Impermanence is a shared theme across philosophies. Stoics counsel alignment with nature's course. Buddhists teach non-attachment, and existentialists urge authorship without guarantees. Cosmology adds a canvas big enough to test those ideas against billions of years. The Fermi question, where is everyone, acquires new nuance when expansion hides distant civilizations and local dynamics dominate outcomes. The silence we hear may be physical, not lonely, a mix of selection effects and the economics of signals over widening gulfs. If life is rare, ethics inherits scarcity. If life is common, ethics inherits solidarity. In either case, a long-lived species faces the same homework: reduce existential risk, grow wisdom faster than power, and invest in institutions that outlast individuals. Earth's habitability window is finite on biological timescales, climate feedbacks, stellar brightening, plate tectonics. So the universe destined for silence begins locally as a mandate to keep gradients generous and ecosystems resilient while we still have abundant starlight. Existence under an expanding sky encourages humility without surrender. Our narratives must be strong enough to steer action, yet light enough to update when new measurements arrive, a balance between conviction and corrigibility, meaning scales with stewardship. To the extent we preserve biodiversity, reduce suffering, and extend the reach of understanding, we convert temporary energy flows into stories that remain legible long after individual lives end. Some worry that cosmology makes purpose small. The counterpoint is that context widens purpose. There is more to care about, more that could be lost, more that collaboration can rescue. So awe becomes a motive, not a narcotic. Anthropic reasoning raises unsettling possibilities. We observe a universe compatible with our existence because incompatible regions cannot host observers. Rather than smugness, the takeaway is caution in inference and gratitude for parameters that allow chemistry to dream. Algorithmic complexity adds another angle. The shortest description of our world is not trivial, and scientific progress compresses that description. Research is thus a moral project of reducing wasted explanation and increasing predictive reach. From neuroscience, consciousness appears as a biological data structure with felt qualities, emerging where information integrates and updates against goals. Valuing life includes valuing the substrates that support such integration: education, health, and environments hospitable to learning. Time preference becomes a philosophical lever. Discounting the far future heavily is irrational if risks multiply. A gentler discount recognizes uncertainty, but still weights future lives substantially, leading to policies that plant trees of both wood and knowledge. In a universe with diminishing external conversation, internal honesty becomes paramount. Societies that can tell themselves the truth about resources, error rates, and bias will navigate narrowing horizons with fewer self-inflicted wounds. Art remains a laboratory for value. By staging possible worlds and futures, it rehearses empathy and expands the policy imagination, enabling choices that are not trapped by the pattern of past mistakes. Religion and metaphysics can coexist with cosmology when they accept shared ground rules about claims that touch the physical world. Beyond that boundary, their poetry can still motivate care, humility, and patience without dictating measurements. Education for an expanding cosmos should teach limits without fatalism, supply thermodynamics, statistics, and systems thinking alongside ethics, so students can see how feedbacks amplify or stabilize choices across ecology, technology, and culture. Dissipative adaptation suggests living systems exploit structure and noise. Perhaps cultures can do similarly, finding opportunity in randomness via robust institutions that flex rather than snap under surprise. A long reflection, advocated by some philosophers, would pause major irreversible choices until understanding deepens. In practice, that means building habits of reversible experimentation, transparent forecasting, and explicit trade-off records. Civilization's archive strategy becomes a virtue. Redundant, open, and geographically diverse repositories of language, science, and art function as lifeboats for meaning, able to relaunch inquiry after interruptions. If cosmic silence is destiny, local music matters more. Communities that cultivate beauty and solidarity increase the density of good experiences per joule, a pragmatic aesthetics of efficiency for finite worlds. Ethics under uncertainty favors moves that are good under many models, reducing violent conflict, preventing extinction drivers, maintaining civic truth markets, and keeping options open for peaceful exploration. Technology policy should be telescopic and microscopic. Telescopic in projecting far-field consequences, microscopic in auditing near-term failure modes. Both views protect value in a universe where second chances may be rare. Biology's lesson is cooperative competition. Ecosystems thrive when niches interlock. Human systems can mirror this with markets bounded by guardrails that force negative externalities into the price, aligning incentives with planetary arithmetic. Justice acquires a temporal dimension. Descendants are stakeholders, intergenerational compacts, constitutional limits on pollution, funding for basic research, protections for repositories, translate abstract care into enforceable commitments. The philosophy of measurement matters because reality resists simple stories, Bayesian humility, transparent priors, and pre-registered predictions reduce self-deception and keep discovery cumulative rather than cyclical. Language should be engineered for clarity about risk. Shared glossaries for uncertainty, confidence, and evidence prevent avoidable polarization and let diverse communities cooperate on problems larger than any single identity. If life on Earth is a brief flare in a long night, its best vindication is quality, not duration. Make the flare wise, kind, and curious. Make it multiply opportunities for other minds. Make it leave fewer wounds and more beacons. Philosophy must keep pace with scale. As instruments expand sightlines and models compress complexity, ethics should absorb update cycles, treating new data as invitations to refine duty rather than threats to meaning. A cosmological stoicism does not deny sorrow. It assigns it context, allowing grief to motivate repair and learning, not apathy, and to link personal losses to the shared project of reducing preventable pain. On the question of destiny, we can distinguish the thermal fate of matter from the narrative fate of value. The first may be cooling and quiet, the second is open, written by choices that accumulate into culture, law, and memory. Simulation arguments, if entertained, complicate nothing essential. The ethics of local experience persists regardless of metaphysical substrate. Suffering is to be reduced, understanding to be increased, promises to be kept. Cosmology's indifference does not excuse cruelty. Rather, it eliminates appeals to cosmic favoritism, leaving compassion and evidence as the remaining legitimate currencies for debate and policy. Perhaps the most humane response to an expanding, eventually quiet universe is to become better at gratitude, for clear nights, for difficult problems, for teachers and rivals, for the rare century of abundant data we occupy. In daily life, this translates to patient competence, fixing infrastructure, educating children, debugging institutions, mundane tasks that, scaled across millions, buffer communities against shocks and preserve room for curiosity. Love becomes rational under cosmic arithmetic. Cooperative agents survive and flourish more often than isolated ones. The mathematics of repeated games and reciprocal altruism formalize what poets long intuited. Beauty is not a luxury, it is cognitive fuel, focusing attention and sustaining effort when problems are large and rewards deferred, an energy policy for minds facing long-horizon projects. Hope, finally, is not a forecast but a stance. It commits to action under uncertainty, to revision under evidence, and to kindness under strain, because those policies outperform their opposites over long runs. From here, a closing thought gathers the threads. Expansion separates by increasing distances and diluting signals, yet it creates by generating gradients, new stars, new chemistry, and new informational niches where minds can arise and cooperate. Separation is the price of cosmic architecture. Without stretching space, the early fireball would not cool, nuclei would not form, and the periodic table would not unfurl into metals and molecules that make cells possible. Creation follows in the gaps between densities, temperatures, and potentials, where complexity can catch and hold. The universe writes opportunity in the same sentence as absence. On human scales, separation protects diversity. Distant labs, distinct cultures, and parallel experiments explore different corners of solution space. Creation shows up as innovation that cross-pollinates when paths reconnect. In galaxies, separation moderates violence. Stars too close would sterilize, but at measured intervals they illuminate and enrich. Creation is the long arc from hydrogen to habitats, powered by gradients that expansion itself helped set. For knowledge, separation demands better bridges, standards, translations, interfaces, while creation rewards those who build them, because truth moves slower than rumor and less carried by shared protocols. For ethics, separation challenges empathy with distance. Creation equips us with art, science, and institutions that extend feeling and responsibility beyond immediate circles. For memory, separation threatens decay. Creation invents archives, redundancy, and pedagogy that keep understanding alive across generations. Thus, expansion is not the antagonist of meaning, but its condition. The same dynamics that dim remote lights also free local pockets to try, learn, and try again, writing values into matter while gradients last. Our task is to practice creation without denying separation, to build cultures and tools that find opportunity in constraints, to measure with care, to repair with humility, and to celebrate the improbable fact that a finite world can host infinite curiosity. When the future grows quiet, what remains is what we made with the time and energy we had: friendships, discoveries, works of care, maps of understanding. Each a local victory against confusion that needs no applause from distant galaxies to be complete. So let expansion be both the distance we cannot cross and the room we require to grow. Let separation teach patience and precision. Let creation invite courage. And let life on earth, brief or long, be worthy of its cosmic address.